So we'll continue with our study of properties of convergence in measure. So now we look at some algebraic operations and the usual properties. So let X S mu be a measure space, Fn Gn real valued measurable functions, Fn converging to F in mu, Gn converging to G in mu, Fg real valued measurable. Let alpha beta belong to R, then alpha Fn plus beta Gn will converge to alpha F plus beta G in measure, and mod Fn will also converge in measure to mod F. So these are the usual properties we expect from any reasonable notion of convergence. So proof. So let epsilon be greater than 0. So then set of all x in X such that mod alpha Fn plus beta Gn minus alpha F plus beta G greater or equal to epsilon. And this is contained, of course, you can easily check this. This is a usual trick which we do, less than mod Fn minus F minus Fx greater or equal to epsilon by 2 mod alpha union set of all x in X such that mod Gn minus x minus Gx greater or equal to epsilon by 2 mod beta. So we can take, of course, alpha beta not equal to 0. Otherwise there's nothing to prove. Okay, so then the right hand side, for n sufficiently large, the measure can be made as small as you like, and therefore this measure also goes to 0. Similarly, you have x in X such that mod Fn x minus mod Gx mod Fx greater or equal to epsilon is contained in set of all x in X. This set mod Fn x minus Fx is greater or equal to epsilon. This again by the triangle inequality, mod of mod A minus mod B is equal to less than or equal to mod of A minus B. Okay, so if this is greater or equal to epsilon, this will also be greater or equal to epsilon. So from these two, the result follows immediately. So now next proposition about products. So X S mu measure space, Fn Gn real valued measurable functions, Fn converges to F in measure, Gn converges to G in measure, Fg real valued measurable. Then if mu x is finite, so now we are having a condition here, Fn goes to Fg in measure. So there is some extra restriction in this. So proof. So we know that Fg is equal to 1 by 4 of F plus G square minus F minus G square. So if fn gn goes to f and g in measure, then fn plus gn will go to f plus g in measure, and fn minus gn will go to f minus g in measure. So sufficient to show that fn converges to f in measure implies fn square converges to f square in measure. So then this will go in measure, fn plus gn square will go to f plus g square in measure, fn minus gn will go to f minus g square in measure, and then by multiplication by 1 by 4 you can easily check is also no problem, and therefore we will have completed the proof of this theorem. So now this is done in a few steps. So first step, you assume fn goes to 0 in measure. So set of all x in x such that mod fn square is greater or equal to epsilon is equal to set of all x in x such that mod fn of x is greater or equal to root epsilon. So it's the same thing, so epsilon positive, and therefore this implies the fn square goes to 0 in measure. Step 2, so fn goes to f in measure, this implies that fn minus f goes to 0 in measure. Now you let en equals set of all x in x such that mod of x is greater than n. Then en decreases because as n becomes larger, the set becomes smaller, and since f is real valued, it decreases to, so f is real valued. This decreases to the empty set. So now you use the fact that mu x is less than plus infinity, and this implies that mu of en goes to 0. This is the continuity from above which we have proved. If you have the finite measure space, then you have the intersection. If en decreases to empty set, then mu of en goes to 0. Okay, so then choose, so given delta positive, choose m such that mu of em is less than delta. Now set of all x in x such that mod fnf of x minus f square x greater or equal to epsilon, this is equal to set of all x in x such that mod fnf x minus f square x greater or equal to epsilon intersection em union set of all x in x such that mod fnf f x minus f square x greater or equal to epsilon intersection em complement. So that's a straightforward thing. So now so if this set, so set of all x in x such that mod fnf x minus f square x greater or equal to epsilon intersection em, the measure of this set is obviously less than the measure of em, and therefore that is less than delta. Now on em complement, fx is less than mod fx is less than or equal to m. Therefore you have mod fnf x minus f square of x Mod is less than or equal to so epsilon less than or equal to that is the thing. Now that is less than or equal to mod f is less than or equal to m times mod fn x minus fx. Therefore, set of all x in x such that fn f x minus f square of x greater or equal to epsilon intersection em complement is contained in set of all x in x such that mod fn x minus fx is greater or equal to epsilon by m, and this measure of this set goes to 0 because fn converges to f in measure. So fn converges to f in measure implies there exists a capital N in n such that for all n greater or equal to n you have the measure of set of all x in x such that mod fn fx minus f square x greater or equal to epsilon, that is less than the measure of this, and that can be made less than delta. So consequently, for all n greater or equal to capital N, you have set of all measure of set of all x in x such that mod fn f x minus f square x greater or equal to epsilon is less than 2 times delta, and so that implies that fn f converges to f square in measure. So step 3, you have fn square minus f square is equal to fn minus f whole square. So that's fn square plus f square minus 2 times fn f minus f square. Plus 2 times. Okay. Now this goes to 0 in measure because fn goes to f in measure. The square, when it goes to fn minus f, goes to 0 in measure, so the square goes to 0 in measure, and just now we saw that this goes to 0 in measure, and therefore you have fn square converges to f square in measure. So this completes the proof of this proposition. So example, so not true if mu x is plus infinity. Okay, so again you take the standard set x equals n, s equals power set of n, and mu equals counting measure. Now you define fnk equals 1 by n if 1 is less than or equal to k less than or equal to n, and 0 if k is bigger than n. Then this implies that fn goes to 0 uniformly, implies fn goes to 0 in measure. We have seen that. Okay. Now you take gn equal to n for all n, and so gn you have a fixed sequence, you don't even have to need the sequence. Now fn gn of m equals 1 if at n will be 1. So this will mean that fng does not go to 0 uniformly. So fng does not converge uniformly to 0. Hence, FNG does not converge to 0 in measure. Okay, so this is not true for infinite measure spaces. Okay, so we will conclude our study of convergence issues with this, and before proceeding further, we'll do some exercises.